get started here. Just sort of stunned. This is our last regular class period. As you know, we don't have class tomorrow, but we have our fourth exam Friday, 1:10 p.m. in the Uri Lecture Hall. Katie, did I see you up there somewhere? Did you want to say anything?
Yeah, I just want to quickly mention, if anybody thinks that they are going to be unable to make it to the exam on Friday for any given reason, whether they're in quarantine or they're feeling ill or whatever, just make sure you or let us know sooner rather than later. We do have the ability to offer the exam on Moodle, so if that needs to be something that you need to take advantage of, just make sure you reach out to us and let us know.
Thanks, Katie. And I'll now ask if people have any questions at this point. And I'm sure we'll be, pushing it when we get to the end of the hour today. I'll try to stop anyway at a certain point so that we can have questions then. But if anybody has any questions right now, I'd certainly entertain those. All right, well, we deal with toxicology all the way along in this course, but I like doing a segment that's devoted to some things which are a little bit, related but different than sort of typical pharmaceutical-based toxicology. These lectures, we could make a whole semester of this or 1 hour, which we're going to do today. So there's lots on this PowerPoint presentation, which I'll skip over. I know exactly what I asked relative to toxicology on the exam, so we need to make sure that we've done that. And if there are little bits of pieces along the way here today in which I skip over too fast and you're interested in it, want to do something more with it, let me know and I can give you some guidance along those lines. So if there aren't any more questions right now, I'll go ahead and get started. Friend of the family, the dog was doing a little fetch with pine cones. I thought that was pretty cool. How about those paws? That's something. So somewhere along here, maybe there's something that can help keep you relaxed today. I know it's intense. So, some of the things on our outline here are things that we can skip over so rapidly because clearly we've been talking about pharmacokinetics and dose response all semester long. So the things that are on here aren't anything beyond that, and maybe aren't even as far as we went in a number of those areas. But certainly these areas are as important to toxicology as they are to pharmacology in general. Couple of our cats all snuggled together there. Earlier in the day-to-day, one of them was with me here on the couch and just burrowed under a blanket and went to sleep. This is perhaps my favorite one of all time. And I wish I could lay claim to this slide. I mean, it almost looks like we could. It almost looks like our cats, but it wasn't ours. It was somebody gave this to me. And great idea there. It's where I keep my spare cats. There's the crew, relaxing. Saving up energy so they can study for an exam, I'm sure. Well, IUPAC a few years back put together a glossary of toxicological terms. And being from IUPAC, of course, it's geared toward chemists. And in fact is sort of intended to be a helping hand for chemists who are interested in toxicology but don't necessarily have the specific training in that regard. So it's a highly oriented sort of chemical index. But if anybody is interested in this, I have a copy. Let me know, and I'll share that with you. In fact, I think I've got it in computer format somewhere around it, as well as a physical format. So it's an interesting look at terminology for the language of toxicology. For many years, I led into this discussion with the problems that were going on in Flint, Michigan. I didn't have a picture of Flint, so I put Detroit, which is a little bit south of Flint. For you Michiganders or others out there, that's Renaissance Center that you're seeing there about mid photo, and this is a little bit east of Renaissance Center in Detroit. The problems with lead in the water supply at Flint is classic toxicology, and a little bit sobering to think that I was looking at a magazine that we had from that era. That was 10 years ago that first started, and then all the problems started cropping up in Newark, New Jersey, and elsewhere with respect to lead also. So I talked about this a little bit in our general toxicology, but there's sort of a new environmental problem that I want to talk about, and I'll as a current event, I'll bring that up a little bit later. So the lessons which we learn from Flint and Newark and other places is that even though lead toxicity, the knowledge of it is ancient, going way back into millennia ago. We're not done with lead by any means, and there are various sites of contamination throughout the world, some of which have started to clean up, and some of which are not as prominent as they used to be, but they're still there. There's still some lead pipes. There's still some lead paint out there, although again greatly reduced. We've stopped using leaded gasoline in this country anyway, by utilizing fuels which are a blend of hydrocarbons to reach sort of the same anti-knock characteristics of leaded gasoline. Lead is still around as a problematic thing. You can have acute lead poisoning, although it's not, excuse me, near as common as more chronic exposures to lead are concerned. And this is a real issue because the adversities to lead are widespread, as you can see on this particular slide. And I would like to note the nervous system especially, and particularly in the context that lead is a problem associated with developmental neuroscience. So as a young brain is developing, it's very susceptible to lead and other heavy metal contamination. And, it's just stunning to think about the thousands of small children that were exposed to lead in Flint, and the impact that this is going to have in terms of their brains and of course other organs as upcoming years unfold. Still, many people don't trust the water supply in Flint, and they're still drinking out of canned bottled water, and I don't blame them for being suspicious. It's been a horrible situation. Hard to trust government and other regulatory agencies when there was such a failure as there was there. But it doesn't take Flint, Michigan, or Newark, New Jersey. Environmental considerations are important everywhere, whether it's Balboa Park in San Diego, the Rattlesnake Creek here in Missoula, or various other sites. So we have to try to develop a consideration of problems that we may be introducing into the environment in a variety of locales. And one of the things that I say about uh, toxicity of this sort is that once you have it, you have it. Um, you make up a adverse substance. You may move it from one uh, garbage spot to another, but you still got it in this world. And you got to be careful about what you make in the first place. Let me pause for just a moment and ask, did I bring up the screen, share screen this time?
Yeah, we can see
You
everything.
can see it, okay. Don't want you to miss out here. Our perspective on adversities changes over time, of course, just like it does throughout the whole realm of pharmacology. And uh, don't want you to memorize this slide, but I just put it on here because there was a time, and not that long ago, when benzene was basically just considered to be a solvent, which it is. It's a great solvent, but it was not really considered to be unusually adverse until the fact that it's a carcinogen was was developed. And so in 2020, you don't see near as much benzene around um, as as in the past. Relative use of benzene were introduced as substitutes for it, such as toluene, but you know, you've got adversity there too. So again, once you've got these things, you've got them. Goodman and Gilman, first edition, lots of heavy metal based compounds in the therapeutic realm, including the arsenicals listed on this particular page. Now, we, of course, in 2020 still use, for therapeutic reasons, a lot of toxic substances. And I'm sure 100 years from now, we'll look back on this era and go, oh my gosh, hard to believe that we were using that substance for therapeutic purposes, because it's really a poison. But we do change our minds about the chemical and pharmacological nature of things, and that will continue, I'm sure, and something that's a little bit difficult to keep track of. Well, chemical toxicology is not only a situation with the synthetic world and so on, but with the natural product world, and or organisms like snakes are a component of the toxicological realm. Here's a story from about 15 years ago, unfortunate, tragic story that I just use as a thought-provoking slide in our presentation here. Spiders, snakes, spiders, marine organisms like cone snails are tremendous sources of toxicological and, as we've talked about a little bit, pharmacological agents. Plants of various varieties all over the world. Ricin is a fairly commonly encountered toxin. It's a component of chemical biological warfare arsenals throughout the world. I'm sure Katie could talk about this probably better than I can. But ricin is an extract of castor beans, and you know, it takes a lot of beans to come up with the white crystalline solid that ricin is. But once in a while, we still hear about it in the news as somebody opens up an envelope that came through the mail with a white crystalline substance in it, and what is it? Is it cocaine? Is it sodium bicarbonate? Is it ricin? It has to be tested, of course. And one thing that's a little bit unusual about ricin is that its mechanism of action is fairly well understood. Um, and so I'll just let you read about how ricin inactivates ribosomes. But you can well imagine that with something like a ribosome, which is important across the lifespan or across living span of nature, you've got a very serious poison in this substance. Um, Hard to do anything about it too, other than making sure that one doesn't come into contact with it if you possibly can. Might even be an exam question on rice, who knows. And toxicological things are, any living form is subject to adverse substances. And whether it's a dog or a cat, some marine organism, human beings, famous or not, we have to take considerations of adversity. And although some of these things have been reduced in our world environment in recent years, in other ways, certain other things are increasing. So there's really a lot of concerns out there about ecotoxicology. Where we encounter substances varies a little bit depending upon a variety of parameters. Here's an older table, but the message is pretty well the same. If you're a young, you're a child, you may encounter adverse substances via drug things, but also things just around the house, cosmetics, cleaning substances, household substances, things you find in the garage or the workplace, the workshop, are all potential sources of adversity for young people as well as adults, of course. Slip this in to show the dramatic changes that occurred in the environment. Excuse me. When we got rid of leaded gasoline, and you can see the really precipitous drop in environmental levels that occurred as the result of that. So that's been an awfully good change there. Adults are more likely to be poisoned by drug substances than household things, but the household things and the natural product things and so on are still there on the list, regardless of your age. And it may differ a bit geographically, but many of these things are found as problematic throughout the world. And again, any living form, no surprise to you folks, can be subject to poisonous substances. A real heartbreaker has to do with the poisoning of dogs and cats, some of which is inadvertent, but some of which is purposeful. And sometimes people who have a hard time with dogs set yummy food out there that's contaminated with some poisonous substance for their unfavorite dog, and then you have a real tragedy. You've heard about this, and we need to be concerned about this worldwide. There are at least low levels of many drugs in their metabolites in water supplies throughout the world, including in the state of Montana. And as pharmacists, you folks need to help educate our public about the contaminating aspects of drugs and metabolites. Environmental burden is a terminology that's utilized by some people to basically account for encounters in the environment that we have with toxicological substances some of which may be there in very small amounts. But what does this mean in terms of combinations? If we encounter a contaminated water supply that has 200 trace substances in it, what is the sort of the aggregate of that toxicity? We don't really know the answer to that question at this point, and there's got to be a lot of research done in this regard. But the number one thing we need to do is try to keep these substances, out of our contact zone, and then not have to deal with it to clean up if we've not contaminated things in the first place. This is where this sort of current event comes in, and I could ramble on about this the rest of the hour, so I'll try to keep it as short as I can. But I ran across this article in the Los Angeles Times from just a little ways back this fall. And like probably all of you, I get these services that supply me with interesting articles. And this, I try to not read these too much because the impact on time can be substantial. But I saw this one out of the Los Angeles area that I thought I would read, and I was stunned and disgusted, I guess, maybe at the same time after reading this particular article. Those of you who are familiar with the geography of Central and Southern California may be aware of a series of islands just barely off the coast known as the Channel Islands. And some of these are really, really close by, such as, at Ventura, a typical day on the beach, you can see the Channel Islands there very, very readily. Or off the coast of Los Angeles, Santa Catalina is perhaps the best known of the Channel Islands, and it's a big one. And a lot of times there's a marine layer of fog out there, and you can't see it real well. But on clear days, from even a little bit north of Los Angeles to almost the San Diego area, you can see Catalina, and sometimes it looks like it's just about a few feet out there. It's so big. And a little farther to the south, San Clemente Island is, I think, the last in the chain to the south, and pretty much about 30 miles or so off the coast from the Southern California town of San Clemente. But anyway, Catalina is our focus of this news item, and it has to do with pesticides, and especially DDT. And the actual stunning thing about this particular instance is that DDT was banned in the United States decades ago. I think it was even in the early 1970s, perhaps, that DDT was banned. But there was a company in the Los Angeles area, not far from Los Angeles International Airport, which was a major producer of DDT during the time that we were still making it. And interestingly, the company continued to make it for a while, even when it was banned in this country, because it wasn't banned elsewhere in the world, and we hadn't banned sales of it at that point. Again, those of you that are familiar with the geography there know there's a part of coastal Los Angeles known as Palos Verdes, and the company from the nearby site of their synthesis, which LA International is close to Palos Verdes there, and they ran a little pipeline out through Palos Verdes into the ocean, and waste that they had, they just poured it out of the pipeline into the water there, under the idea that, well, the ocean's big, and if you just dilute it out in the ocean water, everything's going to be okay. Well, everything was not okay, and that site of dumping from that particular pipeline um, became one of the largest Superfund sites in the United States, which in Montana, we can all relate to, I think, because of Libby and because of the Butte Anaconda um, area. But eventually, EPA listed this site as a Superfund site, and so the dumping of the DDT waste and related PCBs uh, was stopped. Um, well, it was stopped as far as the pipeline was concerned, but it wasn't stopped beyond that, because what they started doing was loading the contamination into large barrels, putting it on barges, and then in the darkness of nighttime, 2 o'clock in the morning, that sort of thing, um, uh, heading out to the continental shelf and dumping off the barrels into the water. And even though they're supposed to go way out to the continental shelf, they shouldn't have been doing that either. But um, a lot of times at night, or rather than going that far out, they would just stop somewhere. It's about if you know the song about Santa Catalina, it's about 26 miles off the coast of Los Angeles, and so in between Catalina and LA, they started dumping these barrels, and then forgot about it basically, and it was very difficult for the public to know that this had even happened. But in the decades since the dumping occurred, marine biologists of the area, by the way, USC has a marine biological station at the isthmus there at the north end of Catalina, with a variety of scientists working on ecology-related research projects. They kept noting that many marine organisms were suffering from something, and they weren't sure what it was, but they did note unusual amounts of DDT and related substances in the tissues of these marine organisms. But they couldn't really figure out where it's coming from because, again, the pipeline dumping had stopped. But there were rumors out there that these barrels of contaminated substance were out there in the channel. It was very difficult to know whether that was the case or not because nobody was talking. Everybody was keeping tight lips on the thing, but the rumors persisted. And finally, using little research-based submarines and so on, they were able to identify the potential dumping site. And this is particularly sad because the waters of Catalina have long been known for their clarity. And for any of you who have ever been there, you might have taken a glass bottom boat out of Avalon, which is more toward the southern tip of Catalina, but the only major town on the island. And if you don't like doing the diving yourself, you can just get into one of these glass bottom boats and look at the beautiful marine life that's out there in those clear waters. But non-contaminated waters, nope, not anymore. Because it turns out that thousands and thousands of barrels of this contamination was dumped out there, and not surprisingly, a barrel's not going to last forever. They're beginning to leak, and now divers have actually gone to these sites to verify that the barrels are out there. So I thought this was a toxicology story that fits the sort of environmental burden situation, and what's going to be done about it? Nobody knows. They can't figure out what to do. Move it to another site and dump it there? What are you going to do once it's there, and especially at a relatively remote site like this, which is very hard to retrieve? So anyway, you might want to keep that in mind as we think about contamination of our environment. And once you've got it, like with DDT, of course, it's rather stable stuff. And once you've got it, you've got it. So this will be an interesting story to follow and see what happens and what solutions people come up with to try to resolve this particular issue. Very, very, very sad stuff. Well, you can get exposed to substances in a variety of ways, and BPA is an example of a substance that in the past anyway, was heavily utilized as the lining of cans, um, preservation purposes, and if you were eating a canned vegetable or drinking a soda from a canned substance, you may have been exposed to BPA, and we all have BPA in our systems. It tends to partition into fat, and as you can tell from the chemical structure there, and so it doesn't really matter whether you're in Anchorage, Alaska, Missoula, Montana, or somewhere in Europe. You've got BPA in your system. So not wanting to stop coating the inside of cans with substances, the industry brought on sort of BPA relatives that are now used. But what the environmental burden, including the burden to all of us individually, is unclear at this point. But you can certainly encounter things in a variety of different situations. So I'm going to blast through these slides here. We don't need to spend any time on this. We all know that pharmacokinetics is important, if not more important, in toxicology than it is in regular pharmacology. So disposition, dose response. You do sometimes run into some discussion, however, kind of different dose response, and hormesis is one that you may or may not have heard of. It's seldomly discussed, and I'm quite confident that most pharm tox books that you pick up will not mention hormesis, but it's sort of biphasic dose response. You get a hormetic effect with respect to radiation, for example, and very low level radiation actually has some positive benefits, but I mean very low level. And it's a controversial topic. Some people actually don't believe that this sort of dose response occurs, but I do, and therefore I put it out there for your consideration. I mentioned low-level radiation here in the bottom part of this slide. I can't remember if I put a question on hormesis on the exam or not. I have in the past. I think maybe I didn't this time. But beyond that, just in terms of your general knowledge about toxicology, it's I think interesting to know about. So while we're talking about sources of information about toxicology, and I may have mentioned this the first day of class. There's a classic book known as Casseret and Duell's Toxicology, and it's kind of the Goodman and Gilman of the toxicological realm. And if any of you are particularly interested in toxicology, let me know, and I can get an old copy of Casseret and Duell to you, or you can look at a newer one and just borrow it. But probably not right now, since you're just a little bit busy. But standard dose response, of course, is a part of the toxicological realm, as well as the pharmacological. And when Paracelsus basically introduced us to these fields centuries ago, dose response became the fundamental principle of both pharmacology and toxicology at that point. And here's just more dose response stuff. Absolutely nothing new to any of you. Parameters like LD50 have been prominent parts of toxicological lore for a long time. And it's not just LD50, but any of the ED or LD uh, numbers are important as far as our consideration is concerned. Um, Although the one that you encounter by far most commonly is LD50, lethal dose 50th percentile. And the middle of populations are of importance, of course, in a statistical sense, but it's at the extremes and perhaps even the lower extreme where it's most important. And that's where we go back due to the idea of environmental burden. What if we're exposed to a variety of substances, hundreds of them, let's say, in very small amounts? So you have toxic doses to very small numbers may be important things, but still unresolved in terms of our overall understanding of sort of biocidal substances. Well, our familiar targets are a part of toxicology too. So there's our good friends, the G protein coupled receptors, are toxicological as well as pharmacological targets. In second semester 444 Pharm Talks, we have a very prominent section on immunotoxicology as well as immunopharmacology. And in many years, Dave Shepard makes those presentations, and it's real highlight stuff. So I'm not going to dwell on it now because you're going to get such a thorough look at it next semester. But anyway, something to look forward to. Very interesting and ever increasingly important subject. In the workplace realm, often referred to as industrial hygiene, there are a number of special sort of dose response things that are basically time dependent. Is it an 8-hour workday like with the threshold limit value of TWA, or shorter time frames, or no time frame like the ceiling one there, in which you should never be exposed to that level of substances. This is terminology that you run into that sometimes you don't hear that much about in terms of regular toxicology. But the TLV, TWA from a 40-hour work week is a very commonly encountered measure. But I wanted to make sure and get to this last segment because it's historically one of the most important ones. Again, humans were aware of problems associated with what we now call heavy metals for many years going back millennia, and so since all of these substances are still of consideration today, it's important to talk about these a little bit, and we could make a long list of heavy metals. 4 that I've listed here, which I think have historically been of greatest importance, include lead, which we've already talked about a little bit, mercury, really especially in the organic forms of mercury like methyl or ethyl mercury, even more than elemental mercury itself. Elemental mercury is fun to play with in your hand, and it has a hard time getting across the skin, but you still probably shouldn't play with it that way. But there have been worldwide situations with organic mercurials, especially methyl mercury, the problems of contamination in Minamata, Japan are an example of that, and very stable as well as toxic stuff. And arsenic may be sort of the ancient heavy metal, which has received the greatest focal attention as far as its toxicology is concerned. We might not think of iron so much as a poison, because it's, of course, so important in terms of heme-related proteins and enzymes and so on. But it is important poison too, and like anything, you might need a certain amount of it for your successful physiology, but too much of it leads to pathophysiology. So that has to be recognized. Some others that I've listed here: cadmium, copper, which of course is a big deal in Montana and in other places where there's been a lot of copper mining and smelting. Nickel, which is important in terms of chemical toxicology, especially in eastern Canada, and maybe others like platinum that will bear consideration from you folks as well as others in the long run. Taking care of heavy metal toxicity once it occurs is frequently addressed by chelators. And if you recall from your introductory chemistry, chelators are substances, often complex chemically, although not always so, which have relatively high affinity and selectivity for ionic substances. Although the level of specificity is not what we may be familiar with in terms of many of our pharmaceutical interests. Those of you who have worked in biochemical research laboratories or other types of research labs may be familiar with EDTA. It's ethylene diamine tetraacetic acid, and no wonder that we typically abbreviate it with a long set of words like that. So if you want to chelate something in the lab, you may well have utilized EDTA. So, for example, sometimes people want to remove calcium from their samples. They might use EDTA in that particular regard. So I thought you might be, some of you might be familiar with EDTA from that realm of experience. In the toxicological realm, EDTA is one of the most common chelators of lead. But again, since these chelators are not totally specific, other examples of chelators, some of which are listed here, may be also used for lead. But probably the most common and effective use is by EDTA. There's a little bit of a flip of orientation when we think about chelation in terms of the target. The chelator is the target and is the receptor in a sense. So the drug, if you will, is the heavy metal, and you're forming a heavy metal chelator complex, which is subject to elimination. The heavy metals tend to partition into places in our body, like our bone, for example, and therefore they have very long half-lives in our bodies. If you can chelate the substance, the chelator heavy metal complex tends to be pretty water soluble, so you can kick it out in your urine at a much greater rate than you would without the chelator. But again, since the chelators are not totally specific, they bring along their toxicity with them. So it's kind of a tough risk-benefit analysis that goes on in these particular cases. But nevertheless, you will encounter chelators in terms of dealing with heavy metal contamination. This slide here is worth about 4 questions on the exam, so make sure you look at it carefully before Friday. Dimercaprol is commonly used in a lot of different heavy metal areas, but particularly with respect to mercury and especially arsenic. Ferroxamine in the case of iron, and for local interest, copper with penicillamine. Um, uh, Cadmium and nickel are also well complexed by dimercaprol. Uh, so here's just a little bit of additional information about EDTA. I'll let you read that, and a little bit about dimercaprol, because dimercaprol is such an interesting substance from a historical standpoint. This is the already chelated form where arsenic has been captured by dimercaprol, and the historical name for dimercaprol is BAL, or British anti-Lewisite. You know, where does a name like that come from? It comes from the fact that Lewisite is an old arsenic-based chemical warfare agent. So British anti-Lewisite, or BAL, was targeted toward the arsenic-containing Lewisite itself. What are the mechanisms of action for dimercaprol? And one of them has to do with the excuse me, what is the mechanism of action of Lewisite itself? Has to do in some cases with inactivation of lipoic acid, which you may be familiar with from biochemistry, because lipoic acid is not only an antioxidant, but it's also a component of the mitochondrial pyruvate dehydrogenase complex, which is a big deal, as we all know from our knowledge of intermediary metabolism. So I thought I'd bring that up because I thought you might possibly remember lipoic acid from biochem, and just showing the continuity between our subjects, chemistry, especially organic and biochem, medicinal chemistry. All of this is working together in terms of our knowledge of things, pharmacological and toxicological. So British anti-Lewisite or dimercaprol, of course, is a little bit toxic in its own right, because you have to be careful about chelating something other than arsenic. And going back to EDTA for just a second, usually EDTA is loaded up with something like calcium ahead of time, so that you don't end up chelating a bunch of calcium in your system, as well as lead. And of course, we know how important calcium is to a variety of functions, including cardiac muscle and other components of our normal physiologies, such as the nervous system. So anyway, that's it. It was fast, but we covered it. There are a few questions. I think I basically indicated what those were along the way on the final exam, which is not a comprehensive final, by the way, but which is our fourth but nevertheless a final exam. So any questions on this or other subjects, be glad to deal with. I know we're out of time. Katie and I will stay on board here for a little while in case anybody has any questions. And if you do get some questions beyond today, let us know about that tomorrow or early on Friday. Thanks a lot, everybody, for a great semester. You've been a wonderful group. I'm going to miss you a lot here over the upcoming month. But Katie and I will be back with you, as well as a number of other people, including Doug Coffin, who will be the main speaker early on, as well as the main coordinator of 444. So I'll stop now and see if anybody has any questions.
Have a good break.
Thank you.